All right, class. Today we're going to talk about rational functions. Our goals today are to discover what is a rational function. We're going to talk about graphing rational functions. We're going to look at, in particular, the long-run behavior of rational functions, which are horizontal asymptotes, the short-run behavior, which are the intercepts, both the x and the y intercepts, and vertical asymptotes. And then we're going to talk about some sample problems. Some typical sample problems we will see are making sketches of rational functions based on the equation, and then also finding the equation, working backwards, finding the equation based on the graph, getting an equation that behaves somewhat like the graph as close as we can. So to start off, let's look at rational functions. A rational function comes from polynomial functions. If you add two polynomial functions together, you'll get another polynomial function. If you multiply two polynomial functions together, you'll get another polynomial function. If you subtract two polynomial functions, you'll get a polynomial function. But if you divide two polynomial functions, you'll get a rational function. So a rational function is a function made up of a polynomial function divided by another polynomial function. That's kind of the main thing. You've got something like, you might have a rational function that looks like x squared plus 2x plus 3 divided by x squared minus 4. That's a perfectly fine and wonderful rational function there. You might have a rational function w of x that looks like 2x plus 8, and on the bottom you might have a 7x minus 7. Those are two rational functions. That's a rational function. You have a linear function divided by a linear function in there. What you won't have as a rational function is if you, how about not a rational? We'll add a not a rational function. Over here. So how about k of x equals 2x plus 3 raised to the x power over 1 plus 7x. And the problem with this one would be the 3 raised to the x power. When the x is up there in the variable, it's a different kind of function. It's an exponential function, but it's not a rational function, because that 2x plus 3 raised to the x power is not a polynomial. All right, if you look at graphs of rational functions, you'll see all sorts of different ones, and calculators typically have a real hard time graphing rational functions. But a couple of features that you'll tend to see on a rational function is that they'll have some sort of, frequently they'll have some sort of horizontal asymptote. The long-run behavior of your graph, as you head out towards infinity in either direction, you'll approach some number quite frequently. And so you'll have a horizontal asymptote there that you're getting closer and closer to that number, but you never quite get there in the long run as you approach infinity. Occasionally you'll have a student say something like, well, a function will never cross its asymptote, and that's not exactly true. It's possible to have a function that's a rational function like this one, where I've got my horizontal asymptote here, and the function gets closer and closer and closer to it out here, and it never touches it out here to the right, but it can possibly touch it in here towards the middle. In the short run behavior, you might cross that intercept, but in the long run, as you go out into very large values of x, you're going to have you're going to get closer and closer to some number. You can also have vertical asymptotes, so you can have an asymptote that's vertical instead of a horizontal one where you're going up and up and up, or down and down and down on one side or the other of that. But it is also possible to have rational functions that have neither vertical asymptotes or horizontal asymptotes. You can have a graph that sometimes does something like this. It might go off something like that direction. Well, maybe not like that. But you can have a graph that will might just have a horizontal asymptote, might have no vertical asymptotes. Or you might have one that has vertical asymptotes and no horizontal asymptotes. You can get a function that goes something like this, maybe, that has a vertical asymptote at maybe 0, but horizontally is not approaching number. It keeps going up and up, but kind of levels, I don't know, looks like that too. So very interesting things. We've got horizontal asymptotes that are going across left to right, or vertical asymptotes that are going up and down. There might be a vertical asymptote in here as well, and one in here there too as well. So that's some sort of things. Because of these asymptotes, a lot of calculators have difficulty graphing them, and so this is something that we kind of have to get into our minds of what these things look like. It's very possible to graph these on your calculator and miss an asymptote, or get some really weird stuff going on where you miss asymptotes. Anyway, that's the big thing, especially the vertical asymptotes. The calculator tends to miss those. Calculators are getting better about dealing with asymptotes, but it's still a possibility that it comes across and you miss those asymptotes. Okay, but the long run behavior, you're looking at, can I move that down? I'm not sure I can move that down. Anyway, long run behavior, you're looking at what's happening to a polynomial function. So if I just take a polynomial function, well, you want to look at a rational function, which is some polynomial function divided by another polynomial function. What we want to look at is what happens in the long run. What happens as x goes to infinity? Or as x goes to negative infinity. So if I look at something like r of x is equal to 3x squared plus 4x plus 1 over x cubed plus 6x squared plus 2x plus 1. When we talked about polynomial functions, we talked about how the overall long run shape is most influenced by that leading term. And that's still going to be the case in this rational function. Those leading terms are really going to determine. So as x, the shape of what happens. So as x goes to infinity, when I'm looking at 3x squared over, what's going to be important is the 3x squared over x cubed. R of x is going to look kind of like the 3x squared over x cubed, because in the long run, what matters on top is the 3x squared, and what matters on the bottom in that polynomial is the x cubed. Of course, 3x squared over x cubed is going to simplify in the long run to something like a3 over x. And so that's a nice function. That's not a power function, and we know what happens with the power function y equals 3 over x. In the long run, it looks something like this. This was the 1 over x, or the a number divided by x sort of polynomial. That power function looked like this. And so as x goes to infinity, it's going to taper off here. It's asymptotically going to get closer and closer to 0. So what would happen, we would say it as x goes to infinity, r of x goes to 0. We'll use this arrow there to indicate that we're heading to 0. And as x goes to a negative infinity, r of x also tends towards 0. Our value gets smaller and smaller, right? Because if you think of that, 3 divided by x, if you have 3 pies and you divide it by lots and lots and lots of people, each person that you're going to get, each person gets smaller and smaller, gets closer and closer to 0, the more people you have. And so that's what's going to happen there. So that's what you look at, is you look at those top powers of x and say what's going to happen. As another example, if you look at r of x equals 5x squared plus 2x plus 3 over x squared minus 4x plus 7, the long run behavior we're going to look at as x tends to infinity, we're going to look at r of x will look a lot like just the 5x squared divided by x squared, and in this case the x squares will cancel out, and so r of x will look a lot like 5. And it really doesn't matter in this case whether x goes to positive infinity or x goes to negative infinity, because you're squaring that number. If it's a really large negative number and you square it, it turns out to be a positive number anyway. So you're looking at 5 times a really large number divided by that same number, so it's going to approach 5. So as x tends to infinity, or as x goes to negative infinity, r of x approaches 5. You're going to have a horizontal asymptote at x equals 5. Okay, and one more maybe example here. If you've got r of x is equal to, how about x cubed plus 5x squared plus 2x plus 1 over x plus, how about 3x plus 8? 3x plus 8. The long run behavior again. I want to look at what happens as x goes to infinity. R of x is going to behave like the x cubed over 3x. And that's going to behave like just x squared. If you reduce that, x squared over 3, and y equals x squared over 3, that's going to be a kind of an overall parabola U-shaped. So as x tends to infinity, I know that r of x will go to infinity, and as x goes to negative infinity, I'm going to expect that overall U-shape in the long run. R of x will approach negative infinity. It won't actually have a horizontal asymptote. You're not approaching a single y number there, but you can kind of describe what the long run behavior of that function is. Again, no horizontal asymptote. You're not approaching a fixed number. You're not getting closer and closer to 0 like we had up here with our first example, or closer and closer to 5. You're getting closer and closer to kind of this parabola U-shaped. So you're not approaching a number, you don't have a horizontal asymptote, but you can get an idea for what that graph is going to look like. Alright, I think I'm going to stop my first video there, and we will pick up with this with another video in a bit.